Alright, so the last type of application we're going to look at before we move on to sketching is some optimization problems. So if you want to pause the video for a second for people to copy the question down, then you can. Alright, so hopefully you had a chance to consider this. And if I was there, we'd actually probably do this up in the whiteboard so you can do some thinking. But regardless, we're going to move on. So a rectangular field is enclosed by 300 meters of fencing along 3 of its sides. The 4th is a river, so we don't need a fence along that side. Determine the dimensions in the area that will maximize the area of the field. So I have a rectangular field here. We don't know if it's going to be that shape or not. It could be much narrower, it could be skinnier, it could be more like a square, all this sort of stuff. But what we have to do is figure out how to maximize the area. So we need a function that describes the area. And to help you on this side, I'm going to suggest that we've got 300 meters of fencing and we don't know any of the dimensions. So I'm going to start by calling this side x. That's one of my unknown. And if that's x, then of course this side in a rectangular field is x. And the thinking part would be to recognize that there are 300 meters of fencing in total. So we have 300 that's going to go on these 3 sides. We already know, so to speak, what this side is. It's x, and the other side is x. So what we have left over must go over here. So this would be 300 minus this x and this x, which is 2x. So if this was, for example, 20 meters, so we'd have 20 and 20 would be 40. We have 300 meters left over. 300 minus 40 would be 260. So we have this. Now, what we need, though, is a function that describes how to find the area, because that's the thing we need to maximize. So we need an equation that describes that. And of course, in a rectangular field here, the area is found by taking the length times the width. In this particular example, our length we've called 300 minus 2x, and our width is just x. And there is a function there that describes it. Of course, we can rainbow this, rainbow the x, and we get 300x minus 2x squared as a function that describes the area. And now we get to do a little bit of calculus. We want to know when that area is the biggest. So of course, we know from all the examples we've been doing this unit, we're going to differentiate this function and set it equal to 0, because the max area will occur when a prime is equal to 0. So good news is this differentiation is pretty easy. A prime is, so the derivative of 300x is just 300. The derivative of negative 2x squared is 4x. We set this equal to 0. Solve for x, so I'll add 4 to both sides. And we get x equals 75. So that's the value for x that's going to get us the biggest area. Now, of course, we have done some math. We got to go back and make sure we read the question here and answer it. So we got to determine the dimensions and the area that will maximize the area of this field. So I have one side is x, so that means this side is x. So if x equals 75, then this side is going to be 300 minus 2 times 75. 300 minus 150 is 150 meters. So therefore the dimensions are 75 by 150. And of course, to figure out the area then, the area is going to be 75 times 150 is 11,250 meters squared. So actually answering the question then, max field is 75 by 150 meters with area as 11,250 meters squared. So hopefully you'll agree that this question, the calculus involved in this question is not too difficult. The only trick in this is, well, not trick, but the hard part is coming up with an equation or a function that we can differentiate. And it goes back to the question here that says we want to maximize the area. So since area is the thing that we are maximizing, we need the function for area. So once we have this equation here, which boils down to this, we can differentiate set equal to 0 and then select the rest of the equation. So that's example